A gas undergoes a process P is equal to P naught minus alpha V, where P naught and alpha are constants. At what volume will the gas entropy will have maximum value? So here we are not talking about the change in entropy between 2 points, but we are saying that on this line, so this is the plot of P is equal to P naught minus alpha V. So at what point on this path, so on what volume will the entropy be maximum? So our approach here is, we are going to take one random point, and relative to that random point we are going to calculate the entropy at a general point. So P1, V1 we are going to consider as constants which will fit these values, and P and V are variables which also fit this equation, but these are variables, so we are going to find the entropy in terms of that. So wherever P comes we can replace it by V, so we'll get the change in entropy with respect to this point in terms of volume, and then we are going to differentiate that term which we'll get with differentiate it with respect to volume and get the maximum value of entropy. So let's read what I just said. Let's take a random reference state P1 V1 on the process. Now we can calculate energy at a general state PV with respect to P1 V1 and maximize it. So entropy at P at this point PV minus entropy at this point P1 V1. So this is the delta S. So if we maximize this delta S, that will give the maximum value of that will give the value of volume where entropy will be maximum. So SPV minus SPV is equal to delta S of path A, which we can break in an isobaric line, isochoric line and an isobaric line equal to delta S for path B, like we have done in previous lot of problems. So for path B, we have broken it into two parts. Now we are going to need the temperatures. So here the temperature is minimum, so let's assume that is T. Now the ratio of this temperature is going to be the ratio of this volume for this line. So ratio of this volume is V by V1. So ratio of this temperature is also V by V1. So if this is T, this is going to be T into V by V1. Now similarly, we need the temperature here. So this temperature ratio is the ratio of these two pressures. That is P1 divided by P. So if this is T, this is going to be T into P1 by P. So we have temperatures at all 3 points. So let's write the entropy now. So for path B, for the isochoric line, it is N0 CV ln T upon, so final temperature upon initial temperature. So T upon this, plus N0 Cp ln this temperature upon this temperature. So T will get cancelled in both sides, and we'll get this as ln P by P1 plus gamma ln V by V1. Now so we need to maximize this delta S. So let's just get one variable. So we'll write P in terms of volume. So P will be P naught minus alpha V. So our SPV is equal to SP1 V1, which is constant, plus this quantity is equal to becomes a function of volume. So we need to maximize this. So it's the same thing. Either you can maximize this difference, or you can maximize this entropy of at a point PV. It's going to give the same result because this is a constant. So we differentiate both sides, and we get f dash v becomes 0 when this happens. So we just differentiate this equation, you will get this. So this happens when volume is P naught gamma upon alpha into 1 plus gamma. Now you might be thinking this can be minima also, but it cannot be minima, because by solving this f dash v, we only got one value of volume. And we know the minimum entropy is at 0 degree centigrade. So any entropy other than that has to be greater than that. So from T is equal, from temperature 0 Kelvin, the entropy is going to increase. And if we are getting f dash v is equal to 0, so that means that entropy must be at peak. So we get our answer. All right.